Hi, my name is Arha Gandhi, and this is my Physics Lab 3. This lab had two parts. The purpose of the first portion of this lab was to find the mass of a black hole that a star was orbiting around. The system in this situation is the black hole, and the surroundings were the stars. The second portion of this lab was to create a figure-8 orbit between a moon, a star, and a spaceship. The system was a spaceship, and the surroundings were the moon and a star. Both of these were done during a simulation on GlowScript. Here are the models in this experiment, and you can see a quick look for each of the models. The fundamental principles used in this lab are as follows. Net force, curving motion, and the momentum principle. Net force, which is the most important fundamental principle of this lab, is defined as the sum of all of the forces acting on the system. We can apply this principle to curving motion. Curving motion problems can be solved similarly to drawing a free body diagram. The fundamental difference is that the axes move with the object's motion as shown in the diagram. The net force is the sum of the forces in the direction of p hat and the forces in the direction of n hat. This is an example of a curving motion orbit similar to the forces that we can see in part 1 of this lab. As you can see, the force, F net, is the sum of the components in the parallel and perpendicular direction. This is the formula that I use for universal gravitation. This is a non-constant force that was used a lot during the GlowScript model, and it was used to calculate the net force, parallel force, and perpendicular force in space. The momentum principle was also applied. The momentum principle can be defined as follows. F net equals the change in momentum over change in time. The velocity update formula was applied as well, where Vf equals Vi plus F net over m times change in time. The position update formula was also applied, where Rf equals Ri plus V average times change in time. The main results of this lab were as follows. For part 1, the mass of the black hole was approximately 4.07 times 10 to the 22nd. For part 2, it's really difficult to guess and check and end up in a perfect figure-8 orbit. Here's the part 1 of my procedure. As you can see, here's the code, and since the purpose of this lab was to code all of this in simulations, the procedure was to write the code. You can see that the momentum, initial and final momentum vectors are calculated. You can see that the star's range is calculated by delta V, which is the difference between V initial and V final, and then delta P, which is the difference between P initial and P final, and these were combined to find delta P over delta T, and F net is equal to dP over dt as seen in Newton's second law. Then we calculated dP over dt parallel, as you can see in the code below, and then Newton's second law was used to calculate F net parallel, and after doing that, we just subtracted to find F net perpendicular, and you can see that we calculated the mass of the black hole by applying the universal gravitational equation and solving for m in that equation, and then we printed that value in the code, and you can see that the initial conditions are done by a seed, so you can't exactly see what the mass of the velocity of the initial is, but you can see that the star's mass was 2.0 times 10 to the 30 and initial conditions. Here's a simulation of the lab, and you can see the video simulation running. Here's the part 2 of the procedure. So you can see that this was done in a similar manner in GlowScript, and you can see that first we found the position vectors for each of these, and then we applied the universal gravitational constant to find the forces, and then as per the definition of net force, F net equals the sum of force 1 plus the sum of force 2, and that's just what it is. You can see that we did that for each interaction between the objects, and then you can see that we used the position update formula and the velocity update formula. You can see that the velocity in this situation is, you can see it's updated by F net over m times delta t, and then the final velocity is used in the position update formula because universal gravitational is a non-constant force. And same thing is done for the ship, and you can see that here are the initial conditions for the ship that I used to show what exactly is going on, and then here is the code. And there are several sources of error that come from this. Because it's primarily guess and check, it's really difficult to be able to see exactly what the orbit will be. And as a result, it's not a perfect figure-8 orbit. It's actually nowhere close to a perfect figure-8 orbit. But if we had access to actual computational models and we were able to see this, then maybe we would be able to make a more perfect figure-8 orbit. So here's the what-if of this lab. The net force is an external cause, whereas the rate of change of momentum is the observed effect. And we're trying to see the differences between net force and dP over dt. And while they are equal to each other, the rate of change of momentum is directly observed through changes in motion, and net force is inferred through external forces. And net force is it is absolute in a given time frame, and momentum change can vary depending on the frame. And while they have equal magnitude and direction, net force changes momentum, and it is responsible for that, while the rate of change of momentum describes how the object's motion actually evolves, and the parallel and perpendicular components distinguish between changes in speed and changes in direction. So what does it mean? So if we added the black hole and we were trying to solve for all of this together as a system, then every body would interact with each other gravitationally, and that means that the force calculations would be done for all of the pairs of objects. So there would be 3 of them instead of the 2 that you can see here. And each object exerts a gravitational force on every other object, and the most dominant force would be the force with the biggest mass, and unless the masses are more or less equal, the forces will depend on the mass, and since the mass of the black hole is so much bigger than everything else, the forces towards the black hole will have a larger magnitude unless there's another object in the system that has a similar mass to the black hole. Thank you so much.